Greetings. This session is about pathlines, and we will proceed by first talking about the algorithm Anaqsim uses to trace the pathlines, and we'll look at some general pathline settings that apply to all the pathlines in your plot, and we'll look at the different ways you can lay out starting points for pathlines. Quite a few options there. And then we'll look at how pathlines behave when they pass underneath line boundaries of various sorts. A groundwater pathline is just the path that an average packet of groundwater would follow as it migrates through time. And it's a three-dimensional trace of that path. And everywhere in a pathline's trace, the pathline itself is parallel to the groundwater velocity vector. And this tracing of pathlines is completely different than, say, a solute transport simulation where you account for dispersion, for adsorption onto the matrix of the material, or decay if it's a decaying constituent. Those are all great things and useful for predicting concentrations and so on. And this doesn't do that. This is just tracing the advection, the migration of water molecules. And I suppose you could think of a non-reactive solute like chloride migrating with the water without reacting. Anaqsim traces pathlines in very tiny straight line steps, and each step has a set length that is a fraction of the current plot window. For example, if your plot window was 1,000 by 1,000 meters, say, in length, and you had chosen a fraction of 0.01 for the size of each step, then each step would be 10 units long. 1/100th of the plot window dimension. And the direction that this step takes within the plane of the domain, usually that's horizontal, but in the XY plane of the domain, is based on the simulated linear velocities, average linear velocities, at the start and end of this step. And basically, as you're tracing a path line, you're working in one step at a time. So you always know the location of the starting point. You don't know the location of the ending point. So this is kind of a process with a couple of iterations of stepping out in the direction of the velocity at the starting point of the step, evaluating the velocity at the ending point of that step, and then adjusting the ending point because that will be slightly different than at the starting point. And so you go back and forth a couple of times and home in on a good average velocity for that step. The change in the z direction, which is normal to the domain and generally vertical, is computed based on conservation of discharge using a method similar to what Strock's 1984 paper outlined. And that was just, I believe, for steady state and for aquifers with recharge on the top and impermeable on the bottom. But you could take the same principles and equations and modify them to allow for leakage in and out the top and the bottom. And that's what I've done in Anaqsim. The elapsed time that occurs for each little step is computed based on this equation here. The time taken to make that one little step is equal to the length of that step, delta S, in the horizontal plane or in the plane of the domain, divided by the average linear velocity at that step. So this is just intuition here, makes sense. To illustrate how this algorithm works, consider this vertical profile here where we've got in this area recharge entering the top of the aquifer, and then we have a line boundary that is presumed to be by convention at the top of the domain, and then we have an interdomain boundary over here. So there's recharge over here that's getting into the aquifer. We have an impermeable boundary at this end of things, and we've got a path line in black here. It goes like this, and the flow that's below the path line is this red water that got in over here and is, below the blue water that got in a little bit to the right of the path line. So as you migrate to the right, the amount of the horizontal discharge in the aquifer that is due to the red goes from being 100% to being a bit less than 100% and to being substantially less than 100%. And basically this blue discharge here equals the amount of blue discharge there, and this amount of red discharge equals that amount. So Strock's method is based on kind of quantifying and equating these discharges that are above and below the path lines. So if we go further to the right of this dotted line, we're adding more recharge, these green arrows, and those fall in above the blue arrows and above the path line and above the red arrows. If we're injecting water at this point with a line boundary, that would be the orange water, and we can quantify the rate of injection there as well and add that above the green path lines. That will bump our path line vertically downward suddenly, because to equate the discharges, the gradients on this side and the average linear velocities would probably be higher than they would be on this side, and that pushes the red discharge, which is the same on this side as on this side, the path line separating it from what's above, deeper. And in this area we don't have any recharge going on, so our path line stays level. And obviously the aquifer base is assumed impermeable here. We could have leakages in and out of that, and that would affect the path line elevation just like the recharge does up here. So when we reach an interdomain boundary right here, where the domain to the right has a lower base elevation, the path line has to drop so that the same fraction of flow that is below the path line here and here is the same. Like it may be 75% of the discharge is above the path line. That would have to be the same on both the left and right sides of this interdomain boundary, and that is why this path line has to drop suddenly at crossing that boundary. Here are general path line settings that apply to all the path lines in your model. One is the step size, which is something you specify as a fraction of the plot window dimensions. Another is whether or not to show arrow time markers that show both the direction of flow and information about time intervals. You select an interval for the delta t between adjacent time markers. You can also set the total time of tracing, which generally applies in a steady state model. And you may want to just show like a 2-year capture zone of a well or something. So you could set that total time of tracing to 2 years and trace path lines backwards. In transient models, the path lines can only trace for the duration of the transient simulation, which is sometimes fairly short. So path lines aren't real long, but you can select the start time for tracing of those path lines. And those path lines will trace through the evolving flow field, different flow field at each time step in a transient model. And that's kind of interesting how that can work. Here are some examples to show you the impact of both plot window size and step size on the accuracy of path lines. So the top two rows in this, the top two illustrations in the top row have a large window, this entire model. The lower one is a close-up smaller window, and the left two use a step size of 0.01, so 1/100th of the window size, is the ultimate step size, and here it's 1,000th in these two. So the least accurate is this one up here, and when we do a zoom in on the result in here, which I've cut and pasted in here, you can see it's quite coarse, and you can actually make out the step size there. I'm tracing one particular step right here. So fairly long steps when you get in close and start looking at it near the well, and inaccurate. When we go to a step size of 0.001, so 10 times smaller than this one, but the same large plot window, that improves the accuracy, but you can still see a few corners in here and a little bit irregular step sizes. So if we want more accurate, we can go to a smaller plot window. This plot window, you can see where it falls out here. It goes something like this. It's maybe a fifth the size of the large plot window, and that improves our accuracy quite a bit. And you can see smoother looking, but still you can make out the little steps a little bit here. And then the most accurate one over here uses both the small plot window and a smaller step size, and any hint of corners or straight line steps kind of disappears in this image. So you can control accuracy of path lines with both plot window size and step size. Arrow time markers can be added to your path lines. The left plot here, there are none of them, and you don't have to display them. You can have a pathline plot like this if you like. If you want to see time markers, you select the time interval between successive markers on the plot, and they will show up as arrows like this, pointing in the downstream direction, and the time elapsed between the arrows is the same throughout the plot. So in this case, I have markers every year or 365 days because my time unit that I'm using in the whole model, all the inputs and these plot inputs, is days. So that represents a year of average groundwater travel time and another year to the well. These are path lines traced backwards from the well. So that's 1 year, that's 2 years, and so on. And here's the envelope of 2-year locations, and here's the 1-year location envelope. We could break it down to shorter time intervals. Here's same plot, but a time interval of 100 days for the arrows, and you can see more of them and a shorter time span between them. If you hover over one of these arrows, like in this plot, the cursor's right there, hovering over that arrow, this little pop-up box will display the elapsed time at that arrowhead and some information about its vertical elevation in the model. And that can be quite handy. The total time is something that you set in the general pathline settings, and that is the total duration traced in a pathline, whether it's tracing upstream or downstream. These pathline are tracing upstream from a pumping well, and in this case, I've got arrowheads every 10 years, every year, and the total time traced is 10 years. And these arrowheads here show you the locus of points that are 10 years out from the pumping well. You could change that to 2 years and you'd get a plot that looks like this, and these are the 2-year locations right here. So it's quite handy for some kinds of regulations that have you look at, say, a 10-year capture zone or a 2-year capture zone, something like that. In a transient model, you can specify the start time for the time within the duration of the transient simulation when you want path lines to be starting. So that start time can be no less than 0, which is the start of the simulation, and no greater than the sum total of the time elapsed for the time periods that are in your model. So for example, if you had 3 90-day periods, the total time of the simulation is 270 days, and that would mean that you could use a start time anywhere between 0 and 270 days. And if you're tracing backwards in time, like upstream from a well, you could set your time at 270 and trace backwards to time 0. Tracing forward, you could start anytime from 0 to 270, but the maximum length of pathline would be starting at time 0. The freeze transient pathline setting is a bit of an odd duck. What it does is it traces pathlines through one snapshot in time, the flow field at one of the time steps in a transient simulation, as though it were a steady state. So you could trace indefinitely with that flow field. That's not valid because in the transient simulation, the flow field's evolving and it's only looking like that at that one time step. But it turns out that some water supply well regulations require a simulation like that. I know specifically that in Massachusetts, you need to run a transient simulation where you turn off recharge for a half a year or something like that, and then use that snapshot of the flow field at the end of that drought to trace pathlines. It's not scientifically sound, but that is how the regulation is written, so this proves to be a useful feature just for meeting those kind of regulations. Another useful pathline setting is called capture constraint. And what this does, it only displays the path lines that are captured by some wells or line boundaries that you have pre-selected. And that can be useful to see where is the water coming from, for example, that gets to a well. And I think what people call it the area of contributing recharge can be discerned that way. In this example here, this is a multi-layer model that has a permeable trench right here, much more conductive material in the topmost layer compared to the aquifer that surrounds it. And at the downstream end of the trench, there's a well that's pumping. So it's drawing water into the trench where presumably you might be running some remediation scheme, and it flows parallel in the trench to the well. So the path lines are in this left-hand plot. They're started at a lot of points. These circles right here are points within a polygon area at the top of the aquifer and basically entering as recharge at these points. And some of these points get into the trench, ride in it, and get captured by the well. Others bypass the remediation system, and some others appear to get into the trench, but then leave it before getting to the pumping well. And the vertical profile of these path lines here looks something like this. All the starting points up here at the water table. This is the water table here, and these are boundaries between different levels, different domains in the model. I think there are 4 total. We're only showing the top 3 here. But you can see some pathline traces that get pulled back up into the trench, which is this permeable material up in the top layer. Others, they get pulled up a bit but keep on going, and some that fall out of the trench and keep on going. With capture constraint on for that same simulation, we can look at only those traces that end up at the pumped well. And it's the same plot as this. We've just pulled away and are not displaying these other pathline traces that don't end up at the well. So that's what it looks like in profile. And we don't get these traces that continue on. Pathlines can be traced down gradient or up gradient. The down gradient can be quite useful for showing where water leaving some potential contamination source is headed, or the up gradient is often used to show where water coming into a feature like a drain or a well is coming from. The path lines will trace until one or the other of these 4 bullet point conditions is reached. If you reach the specified path line total time in a steady simulation, that will truncate the path line. If you reach an external boundary, that will truncate it. So if you're going in the downstream direction and water is flowing out of the boundary, that could truncate it. If you're tracing upstream and it's a source of water at the boundary, that could also truncate. If you reach a discharge feature interior to the model, where the path line exits the model, in a downstream traced path line, this could be something extracting water like a pumping well or a reach of a river, or a gaining wetland at the top of a model. A recharging feature can also be a termination point if you're tracing path lines in the upstream direction. So this could be the water table and the recharge at the water table at the top, or it could be an injection well or a stretch of a losing stream, something like that. Anaqsim gives you lots of options for where to start your path lines, and you can do it at a single x, y point in the plane of the domain. You can do it at n points evenly spaced along each segment of a polyline. You can do it at n points evenly spaced around a circle. You can do it at points evenly spaced within a polygonal area. You define the polygon, usually digitize it. And you can do it at endpoints that are just outside of a well's radius. At each of these points, no matter which of these kinds of geometric situations you're doing, at each x, y point, you can have multiple path line start points at different levels. Z in the direction normal to the plane of the domain. So you could start one, at one single x, y point, you could have 10 different path lines starting at different levels in the model. Here's demonstrating both a single path line and line path lines. This is the single path line right here, and that circle is the starting point. The line path lines have 2 segments to a polyline and 10 points in each segment. So this segment's a little shorter, so the spacing between start points is less. And again, the start points are shown with circles. And here are circle path lines where we have n starting points in a circle. So you specify the center of the circle and its radius and the elevations at these starting points. Below, this is an area path line where you input a polygon, which I'm tracing right now about like that, and a spacing for the starting points, which are put on a hexagonal grid inside the polygon. So here's a whole bunch of start points that create these path lines heading to a well here. This slide shows some well path lines, and the way this works, you specify n, the number of starting points, and they are distributed evenly around a small circle that has a radius of 1.2 times the well's radius. So very tiny circle, and the direction of tracing depends on the well's discharge. If it's injecting water, it sends the particles downstream, or the traces downstream. If it's a pumping well, it sends them upstream. And a nice feature is that when you move a well, which you can do graphically just by dragging it in Anaqsim, the path line input moves with it. I haven't talked much about how you specify the starting levels, but this example will be useful for that. Let me just go over what this model is. This is our permeable trench with a pumping well at the down gradient end of it, like we saw before. But in addition, there is a pumping well, or not pumping, injection well upstream of it that is pushing water into the aquifer. And that injection well is screened in layer number 2. The pumping well and the trench are up in layer number 1. And we've got well path lines starting at the injection well and going upstream. And that's all of these. And they end, these circles show the endpoints. They end at the water table where they exit the domain. And that basically is recharge, comes in like this, gets deeper and deeper, rides down in the trench and ends up in the well. So all of these circles show the termination points of the path lines that started at the well. And they started at this depth. Here's the uppermost layer, which is an unconfined domain. And they started 40% of the way down from the top and were sent upstream. So in profile, that packet of path lines looks like this. They ride this way and then rise up. Once they get out of the trench and they're going quite a bit slower, they rise up to the water table because there's recharge coming in the top everywhere there. And so the start level for that group of well path lines would be 1.4, meaning it's in level 1, so before the decimal point, it's level. And 0.4 is the fractional depth within the saturated thickness of that level. So 40% of the way down. And that you can kind of see that we are about 40% of the way down from the water table, which is this blue line up here, down to the base of level 1. The other path lines start at the our well path lines around the injection well, which is screened in level 2. And I've started 2 sets of path lines there, one at level 2.2, one at level 2.8. This is the level 2.2 path lines right here, and that's 20% of the way down through the saturated thickness of level 2 domain, which goes from here to here. This is 80% of the way down. That's the 2.8 start points. And both of them fan out radially and are pushed either up in the case of these upper ones or down in the case of the lower ones, basically by the discharge being pushed away from the screen of this pumping well here. And the ones that go up almost reach the water table, but then are pushed back down by recharge and end up, some of them being pulled up a bit by the attraction of the permeable trench and riding in that permeable trench, but then disappearing and getting out of that trench. I guess that's these path lines here, because they're not in it long enough to be captured by the well. And the path lines that go from 80% of the way down through the well's domain will end up getting down into level 3, a little bit of impact by the permeable trench getting pulled up again here, but then continuing on down. This slide illustrates how path lines trace across line boundaries. And what I've got here is a vertical profile of path line traces. And the path lines are all started a little bit to the right of this plot and sent upstream. Okay, so the lowest path line is this number 1. And when it goes under an extracting line element, the pathline trace jogs down if you're going in the upstream direction, but it's pulled up if it's probably easier to think about it. Tracing in the downstream direction, it's pulled up when it passes under an extracting line element that's in this domain. The assumption is made that the line elements are at the top of the domain, which is generally the case if you have a a trench or a river or a drain or something, it's usually at the top. So Anaqsim makes that assumption, and the amount that path lines are pulled up depends on how deep they are in the system and on the extraction rate perpendicular to the path line. So let's just follow some of these path lines. Path line 1 comes down because there's recharge entering at the top all along here, and it's diving deeper and deeper. It gets to an injecting line element, again assumed at the top here, which pushes the trace downwards. And basically the amount of flow that's below that path line number 1 here is the same as here. And in order for that to occur, the gradient to the right gets steeper and the velocity gets higher to the right of this injection line element, which is what you'd expect. Pathline trace 2 comes along and dives a bit further because the amount of flow below it is bigger coming in, and it gets pushed down further because it's higher up in the system. 3 gets pushed down to here, and there is no path line 4. It originates in the discharge of the injecting line element and then appears here. 4, 5, and 6 all originate at that line element. There would be other path lines above 6, and some of those would be extracted by this extracting line element. 6 survives and keeps on going, but not much above 6. Those path lines would be swallowed by the extracting line element. And then these path lines to the right originate as recharge at the top. Path lines do interesting things when they cross an inner domain line boundary. I've got an example here that shows a domain to the left of the inner domain line boundary, which is right here, which has a higher base elevation than to the right in this domain over here. So if we're coming into that with a path line and 25% of the discharge is below the path line and 75% is above, we need to preserve that same ratio in the right side of the inner domain boundary. And that's the algorithm that Anaqsim uses. It preserves the relative proportions of flow above and below the path line when it goes through an inner domain boundary like this. And because the base elevation jumps, the path line has to jump vertically. So at the very top, a path line tracing right at the very top wouldn't jump at all. But at the very bottom, it would jump by this amount. And the amount of the jump decreases as you go from the bottom up to the top. This is the same kind of algorithm that is used in ModPath, which goes along with ModFlow. And McLean Environmental ran this nice comparison, which I'm showing it right, where they did the exact same thing in Anaqsim as in ModFlow, traced a path line, and they jump at a place where the base elevation drops. And they do it identically because the algorithms are based on very similar concepts in math. When your inner domain boundary merges one layer into multiple layers, it gets a little trickier, but the same principle still applies. A path line that comes into such a boundary with a certain fraction of flow below and above, in this case 40% below, 60% above, needs to maintain that same fraction on the opposite side of the domain. In this example, the upper level on the right side of the inner domain boundary, which is right here, is quite a bit higher hydraulic conductivity than the level 2 domain below it. And because of that, 60% of the total discharge that's going to the right here is above the path line when it's at this position. So 40% of the flow is below it, and the lower domain probably constitutes 35% of that, and this little sliver in here is about another 5%, something like that. So again, pathlines will jump vertically at interdomain boundaries in order to preserve that ratio of discharge above and below the pathline. Here's that Strock 1984 reference, a really clever paper about getting three-dimensional path lines out of two-dimensional Dupuy-Forchheimer domain models. And as I said, Anaqsim uses an algorithm that is based on the concepts that are in this paper, but extended to cases that can be transient and have fluxes at the top and bottom of the aquifer.